I can use this drawing here, as I've been able to draw it by myself, to do the energy level order appropriately. I can now have it in this form to be 1s. You can see the arrow comes down to follow by what next? It's 2s, followed by 2p. Good day to you all there. The topic before us today that we'll be looking at under chemistry is oxidation number. Afterward, we'll be looking at the periodic table of the first 20 elements, and alongside with it, we'll be looking at the electronic configuration in terms of the ring formation, and as well in terms of the increase in energy level, how you can be able to draw different electronic configuration for different elements on the periodic table of the first 20 elements. Do stay tuned. I will implore you to subscribe to our channel in order for you to have everyday information, date to date update from our channel. We implore you to do that so that you'll be able to enjoy us the more. Now, oxidation number. What is oxidation number? Oxidation number happen to be the charges you have on a particular element or an atom. Ordinarily, in neutral state of every atom, when they occur naturally, the oxidation number on them is usually 0. Now, there is a rule that governs how you can be able to identify oxidation number. First thing I'm going to do here is to draw the periodic table of the first 20 elements, from which I'll be able to deduct few things as far as oxidation number is concerned. On the periodic table, I have 8 groups. Hydrogen and helium are placed on group 1 and 8. They are placed there for convenience purpose. So we can now go ahead to draw the periodic table like this. I have my 1, 2, 3, 4, 5, 6, 7, 8. Now, this is hydrogen, this is helium here, followed by lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. These are the symbols of all these set of elements I've mentioned right now. Now, this is group 1. The group are the 1 to 8 information I put on the top A. These are the group. And the period are found on this vertical line like this. The period goes in this order. The group goes like this, the period goes like this. And one important thing about the group is this. All the elements found in each group always have the same number of electrons in their outermost shell. Take note of that. After that, you discover that when I say all the elements found in each group have the same number of electrons in the outermost shell, that one will give them the opportunity to have some characteristics that will look alike. Now, group 1 element here, they have 1 electron in their outermost shell. In other words, group 1 element usually will have 1 as their oxidation number. Now, before I will go further into talking about this group in terms of oxidation number, I want to tell us the rules that govern the oxidation number of a particular element. Number one rule I'm going to give you here is on the oxidation number of simple ion is equal to number of charges on it. Oxidation number of any simple ion is equal to number of charges on it. If I'm talking about simple ion, I'm talking about oxidation number of ions such as Na+, this is sodium ion, which is equal to +1. We can have an example of Cl-, which is equal to -1, and so on and so forth like that. For example, you can also have aluminium 3, Al3 plus, which is equal to 3 plus, which is equal to plus 3. That is the first rule that I want you to take note of. The other rule we are going to also talk about is that in a compound state, when you have element in a compound state, when I talk about compound state, I'm talking about when you have element in forms of a compound. For instance, if you have something of this nature, H2SO4, this is a compound. Though this is an acid, but this is a compound form of a particular set of elements coming together. CaCO3 is another forms of a compound. So these are the compound forms of all these forms of group of elements that comes together. Now, in a compound state, element the element in group 1 and 2 have oxidation number of +1 and +2. In that form, element in group 1 here will have oxidation number of +1. All elements in group 2 have oxidation number of +2 in their compound state. Take note of that. Also, in the compound state, the element in group 7 has oxidation number of -1. These are called the halogens. Those elements that are found in group 7 are called the halogens. Why are all these like this? Now, you can see that element in group 1 has oxidation number of +1, as I have said, and you can also see that they belong to group 1 as well. Also, the number of electrons you can find in the outermost shell is usually 1. The same thing applies to elements in group 2. They have +2 as their oxidation number in their compound state. They also belong to group 2, and the number of electrons that you can also find in the outermost shell is +2. Now, this set of elements in group 1 and 2 are metals. When the metals always give out an electron. When a metal donates an electron, they become positively charged. In other words, those elements in group 7, as I've said earlier, that the halogens, they are non-metals. They are to accept an electron. When they accept an electron, they will become negatively charged. They will become what? Negatively charged. In that sense, those in group 7 needs only one electron to attain the so-called octet structure. Now, another thing that makes this element in group 1 to have +1 element is that the electron that is found in the outermost shell, which is +1, needs to be released. Once it is released to such elements such as element in group 7, for example, if it releases one electron to element in group 7, it's going to make it to become positively charged, leaving behind how many electrons with it? Leaving behind 8 electrons at its outermost shell, and the one electron has been transferred into will also have 8 electrons in its outermost shell. That is the intention of most of the elements we have on the periodic table. All of them want to be stable. They want to attain the so-called octet structure so that they can be able to be stable and be able to form a particular compound. Now, that is the oxidation number of group 1, group 2, the halogens in their compound state. We have been able to talk about that, and we have been able to talk about the oxidation number of element of a simple ion. Now, other forms of rules I'm going to talk about here is the atoms in an uncombined state, whether monoatomic or polyatomic, their oxidation number is usually 0. Atom in uncombined state, either monoatomic. When I say uncombined state, for example, if you have aluminium is in uncombined state. Sodium, this state is the uncombined state of sodium as well. These are monoatomic because it contains only one atoms. Now, for instance, if you have O2, or if you have elements such as atoms such as ozone, that is O3, or you have hydrogen, H2, these are polyatomic because the number of atoms that each of them are made up of is more than 1. In this state of them like this, their oxidation number is 0. That is another rule. The next rule is the oxidation number of oxygen. Oxidation number of oxygen is -2. Now, if you look at oxygen very well, you discover that oxygen is found in group 6. As oxygen is found in group 6, oxygen will need 2 electrons to add to itself in order for it to attain the octet structure of the rare gases or the noble gases. Now, for it to accept 2 electrons, which means that it is 2 electrons that oxygen is going to have in order for it to attain the octet structure. These 2 electrons is the one that makes its oxidation number in its compound state to be equal to -2. Why is it -2? Is because it's going to accept an electron. Immediately it accepts an electron, it becomes negatively charged. But there is a clause there. The oxidation number of oxygen in peroxide. When I say peroxide, I mean the same number of atoms of oxygen combined with another atoms of another element. For instance, if you have H2O2, Na2O2, these are good example of peroxide. In this state of peroxide of this nature like this, the oxidation number of oxygen here will be equal to -1. Will be equal to, let me do the calculation as we check whether it is equal to -1 or not. Now, don't forget that I have said it earlier that oxidation number of compound state of any compound is equal to 0. When you add it, summation of oxidation number of any compound is equal to 0. Now, oxidation number of hydrogen here is +1 multiplied by 2. We are looking for that oxidation number of oxygen here, plus 2O will be equal to 0. So +1 times 2, that will be equal to 2 plus 2 oxygen is equal to 0. So if this one comes here, become 2, 0 is equal to 2 oxygen is equal to -2 because this is +2 here. It comes here, become -2. You divide both sides by 2, you are going to have oxygen to be equal to -1. You can see that oxidation number of oxygen here in its peroxide form here is -1. So if you try to work it out and a question is asked about the oxygen number of oxygen in its peroxide, take note of that. Now, in Na2O2 as well, I want to check the oxygen number of oxygen here. I'm going to have sodium is found in group 1, that's 1 times 2, plus 0, oxygen, that is 2, is equal to 0. You can see that this is the compound state, and when you add the oxygen number together, they always equal to 0. So 2 plus 2 oxygen is equal to 0. 2 oxygen will be equal to -2, where oxygen is equal to what? -2 over 2 is equal to -1. So this is enough to let us know that the oxidation number of oxygen in its peroxide is equal to -1. Now, also need to look at oxidation number of hydrogen. The oxygen number of hydrogen in its compound state, as I have stated earlier, is +1. But there is an exception. There are different exemptions that can happen to hydrogen that can make it to not to be equal to +1. The exception is that when hydrogen is in binary compound with a metal atom, it becomes -1. Let's do that. For example, now hydrogen combining with a compound, an atom like sodium, NaH. Don't forget that this sodium is a metal combined with hydrogen. So let's check the oxidation number of hydrogen. Don't forget that if I add these two together, their oxidation number, if I add it together, it will be equal to 0. Number one reason is this. This is a compound. This is a compound in a compound state. And number two, there is no charge on it. So I can now say that Na plus 1 plus H is equal to 0. H will be equal to minus 1. Or you can as well have oxidation number of hydrogen in the compound state of CaH2. Don't forget that calcium is found in group 2. Adding up their oxidation number together, we are going to get 0. So we can now say that plus 2 plus 2H equal to 0. 2H will be equal to minus 2. Because this plus comes here, becomes minus 2. H becomes what? Minus 2 divided by 2, that will be equal to minus 1. Now, two important things I've been able to bring out here. The oxidation number of oxygen in its compound state, as well as oxidation number of oxygen in its peroxide. Also, I've been able to bring out the value of the oxidation number of hydrogen in its compound state, also the oxidation number of hydrogen in when it is combined or when it's added with a metal atom. That is how you get the oxidation number of them. Those are the rules that govern the oxidation number of different atoms or the elements that are found on the periodic table. Now, we are now going to look at how you can calculate the oxidation number of different elements in their compound state. To calculate the oxidation number of different atoms in their compound state. The first question here says that we should calculate the oxidation number of nitrogen from HNO2. We are asked to find the oxidation number of nitrogen here. Now, in this case here, you can now say that the oxidation number, this is the compound state, and the oxidation number of hydrogen, as we have stated earlier, is usually equal to plus 1. Plus 1 plus, we are calculating that of nitrogen, so let's represent nitrogen by X. So let N be X. So let's add nitrogen by X plus, what is the oxidation number of oxygen in this compound state? Minus 2 times, how many oxygen do you have there? 2 will be equal to, don't forget, the summation of the oxygen number of every compound in their compound state, if they are not having charges on them, will be equal to 0. So we are having plus 1 plus X plus times minus will be equal to minus. Minus 4 equal to 0. So plus 1 minus 4 here, we are having X minus 3 equal to 0. So we are X is equal to plus 3. Therefore, oxidation of nitrogen in HNO2 is equal to plus 3. Oxidation number of nitrogen in HNO2 is equal to plus 3. Now, the second question. The second question says that we should find the oxidation number of aluminium in LaAlH4. LaAlH4. We are asked to find the oxidation number of aluminium. Now, in this case here, you have to consider two facts here. Number one is that look at the element or the atoms that you found here. This lithium here is a metal, aluminum is a metal, hydrogen is found in group 1 as well. Now, don't forget, we have said earlier that hydrogen, when it combines with the metals, the oxidation number of hydrogen will be equal to minus 1. So in this case now, you can now say that Al, lithium here is plus 1 plus aluminium, let Al be Y. Plus Y plus minus 1 times 4 will be equal to 0. The summation of all the oxidation number will be equal to 0. So we are having it to be plus 1 plus Y minus 1 times 4 minus 4 is equal to 0. 1 minus 4, that's what? Y minus 3 is equal to 0. So Y will be equal to what? Plus 3 as well. So oxidation number of aluminium in LiAlH4 is equal to what? Plus 3. Take note of this. What we did here is very important. you can see that it is because this hydrogen here is attached or mixed or combined with the metal aluminum here. That is why we mix the oxidation number of hydrogen here to be equal to -1 according to the rules that we have talked about earlier. Now, the third question says that we should find the oxidation number of sulfur in H2SO4. Sulfur in H2SO4. So let S be equal to S itself. Let's make use of S itself, sulfur itself. So now, in this state here, you can see that it is not a metal that this hydrogen is being combined with. So it's in its compound state. Its oxidation number here will be equal to +1. +1 times 2 plus this is sulfur, S, plus oxygen is how many? -2 times 4. Oxygen 2 is in its compound state. This is not the peroxide forms of oxygen, which will make it to be equal to 0. So we're having 2 plus S plus times minus, -2 times 4 minus 8 equal to 0. X 2 minus 8, we have S minus 6 equal to 0. S is equal to +6. So the oxidation number of sulfur in H2SO4 is equal to +6. Now, another question says that we should find the oxidation number of sulfur in MgSO4.7H2O. This is an hydrate compound. Now, magnesium is found in group 2, and we have earlier been told that the atoms in group 2, in their compound state, their oxidation number is equal to +2. So we can now say +2 plus, we are asked to find oxidation number of sulfur plus sulfur itself plus -2 times 4 plus, you can see there's a dot here. So this 7 is taken into consideration all these water molecules here. So you're having 7 into bracket. Water molecule, if you look at it very well, it is a compound on its own. So in that regard, definitely everything we have here will be equal to 0, because we have said that oxidation number, summation of oxidation number in their compound state will be equal to 0 when there is no charge on them. So this one will be what? 1 times 2, 2 plus -2, -2. 2 minus 2 will be equal to 0. So we're having +2 plus sulfur -8 plus 7 into bracket 0 is equal to 0. So we're having +2. That will be 2 minus 8, that's what? S minus 6 plus 0 equal to 0. So we're having S will be equal to, so this one here becomes +6. So the oxidation number of sulfur in MgSO4.7H2O is equal to +6. So also look at some other question. Let me create some space here. Yes. Looking at some other question, we want to find the oxidation number of chromium in Cr272-. Chromium in Cr2O72-. Now, if you look at it very well, you see that this one is different from those compounds we've been talking about since we started the calculations like this. This is having a charge on it, but others we have done so far do not have a charge on them. So now the calculation of all this will be equal to this charge on it. Anytime you see any charges on any forms of a compound or different group of atom, the calculation of the oxidation number, when you sum it up together, to be equal to the what? The charge on them. So this one will be Cr is what we are asked to calculate. Cr multiplied by 2 plus -2 times 7, that is oxygen. This is in its compound state, is equal to -2. That is the charge that we have up here. So we're having 2Cr plus -14 equal to -2. 2Cr plus times minus, minus 14 equal to minus 2. So 2Cr equal to minus 2 plus 14. So when this one comes, they become plus. So therefore, you now do what? 2Cr R is equal to 12. So Cr will be equal to 12 over 2, which is equal to 6. So the oxidation number of chromium in Cr2O7 2 minus is equal to plus 6, is equal to plus 6. Now, we also need to look at another question here, which is asking us to find the oxidation number of carbon in HCl3 minus. Oxidation number of carbon, that's number one, in HCO3 minus. HCO3 minus. So the oxidation number of hydrogen here, this is the compound state of hydrogen. 1 plus carbon is what we are looking for. That's represented by that C itself plus minus 2, that's oxygen, multiplied by 3, equal to, what is the charge on it? Minus 1. So we're having 1 plus C, 1 plus C, plus times minus minus, 2 times 3 is minus 6 is equal to minus 1. 1 minus 6, that will be equal to minus 5. So we're having C minus 5 equal to minus 1. So when this 5 comes in, it becomes C equal to 1 minus 1 plus 5. Therefore, C will be equal to 4 plus 4. So the oxidation number of carbon in HCO3 minus is equal to plus 4. Now, radicals can be formed either to be either an acidic radical or a basic radical. An acidic radical are formed when a particular values of hydrogen is removed from a particular acid and the remaining forms of atoms that are being combined together in that form will form what is called a radical. And the charges that will be on them will be the number of hydrogen that are being removed from them. For example, if you have example of acid radical now, acid radical, if you have H2SO4. Now, for you to have the radical of this form, the acidic radical of this nature will be SO4 to minus. In that sense, it shows that this particular acid here can be splitted into the positive and negative ions, where we have the 2H plus SO4 to minus. The number of hydrogen here will determine the number of the charges on the radicals as well. So we also have another example of radicals, another example of acidic radical, which can as well be CO3 to minus, NO3 minus. This one is gotten from the HNO3. Now you can see that only one hydrogen is being removed from that. In here, I mentioned that we have also what is called a basic radical. A basic radical are cation, that is positively charged atoms. We have them in this form. We have like this basic radical, Na plus is another form of basic radical, Fe, so ion 2, and so on and so forth like that. Important thing to note is this. These are the so-called anion. These basic radicals are the cations. Cations are positively charged, while the anions are negatively charged. These are the forms of radicals that we have. Now, we need to look at the periodic table of the first 20 elements, and we are going to talk about the electronic configuration in ring form, also in the forms of energy level. Now, this is the first 20 element. Looking at them, the atomic number of these is 1, 2, 3, 4, and so on and so forth in that order like that. We can have the arrangement of this in forms of electronic configuration. I'm going to have the first electronic configuration in form of a ring. Now, the first thing you need to note about the electronic configuration of a ring is that rings, the first ring, which is the innermost ring that is closest to the nucleus, the maximum number of electrons is going to have will be 2. While the other set of rings that follows after, the maximum number of electrons that they will have is going to be 8. If the number of electrons they have is not up to 8 yet, you continue filling up that space until when they get to 8. By the time it is more than 8, you need to form another ring. So I'm going to try to draw the electronic configuration of few of these set of element we have in this first 20 element. Now, for instance, I'm going to draw that one of hydrogen. Hydrogen, the ring form of it will be like this. This is 1 electron. I'm going to draw next lithium. Lithium is 3. You can see 1, 2, 3. That is how you do it. You get the answer number 1, 2. This one is fully filled now. Then you need to move to the next ring. 3. This is lithium. Next is that I want to draw for carbon. Carbon is 1, 2, 3, 4, 5, 6. 1, 2, then the next ring, 3, 4, 5, 6. Now, one thing you need to note about this ring I'm drawing now, you can see that this lithium I draw is in group 1. The number of electrons I have in this is called the outermost shell. The number of electrons I have in this outermost shell is equal to the number of group that they belong to. Also, this carbon is in group 4. The number of electrons I also have in the carbon as well, it's also equivalent to the group that it belongs to. I'm going to pick from oxygen again. Oxygen, you're going to have 2. Oxygen is 1, 2, 3, 4, 5, 6, 7, 8. So this one is 2 already. We're having 6 more. 1, 2, 3, 4, 5, 6. Oxygen is also found in group 6, and the number of electrons that is in the outermost shell is also 6. Now, I take sodium. Sodium. Now, sodium is 1, 2, this is 10. If you count it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sodium is 11, that will be 2, 1, 2, 3, 4, 5, 6, 7, 8. And you count it with this, that's 10 now. 11. That is, you can see that it also have 1 electron in its outermost shell. In its outermost shell, I come to magnesium. Magnesium is 12. The atomic number of 12, that's 2, followed by 8. 1, 2, 3, 4, 5, 6, 7, 8. Once this next shell gets to 8, the next one is for you to fill the next shell. The remaining shell after this sort will have the maximum electron there to be equal to 8. It must not have beyond that 8. So, magnesium is what? Next, 1, 2. That's magnesium for you. Now, the next one I'm going to talk about chlorine. Chlorine is, if you count it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So this will be 1, 2. How many will be the next one? 8. Since it's more than 10, so I can fill this one up. 4, 5, 6, 7, 8. That is now 10. 8 plus 2 is 10. Remain what? 17. That's the 7 remains. 1, 2, 3, 4, 5, 6, 7. So also chlorine belongs to group 7. So I can also now talk about calcium. Calcium, the atomic number of calcium is 20. So I can have calcium to be 1, 2, followed by what? How many? 1, 2, 3, 4, 5, 6, 7, 8. This is 10 now, and we're going to 20. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 now. What do you mean? 1, 2. Now you can see that the number of electrons we find in the outermost shell. When you say outermost shell, you are talking about the shell that lasts outside, is the same as the number of electron, a number of the group that each of these elements belongs to. Another thing you need to know there is this. Look at the period. You discover that by the time you draw the electronic configuration of all these elements, you will discover that all the elements in each period have the same number of ring. This period 2, all of them will have ring of 2. Period 3, period 4, we have all the ring to be equal to. That, for instance, we have the sodium 1, 2, 3. All of them will also have 4 there, and so on and so forth, like that. That is the ring electronic configuration of each of these elements. Now, I want to look at the increase in energy level electronic configuration drawing. How do we draw the energy level of electronic configuration? There's a rule that we need to follow, which is called the Hubble's rule. The Hubble rules is gotten from where the arrangement of how electrons are filled into the orbital. These Hubble rules have a particular design that it normally follows. So we're going to look at that design now. Now, the design of energy level is in this order. You have this 1s. This is going to follow the trend of SPDF. 1s, 2s, 2p. When you want to draw this, make sure that they are in order and also in a straight line. 3s, 3p, 3d. I'm doing SPDF. Don't forget. 4s, 4p, 4d, 4f, 5s, 5p, 5d, 6s, 6p, 6d, 7s, 7p. I can have it in this order like this. So I can have it this way. You can see that I show that that arrow is coming down. Let me stop it here. This is the arrangement of the energy level, and I can use this drawing here as I've been able to draw it by myself to do the energy level order appropriately. I can now have it in this form to be 1s. You can see the arrow comes down to follow by what next? It's 2s, followed by 2p, followed by 3s, followed by 3p, followed by 4s, followed by 3d, followed by 4p, followed by 5s, followed by 4d, 5p, 6s. So let's stop it there. Now, important thing again to note here is that the maximum number of electrons that this each s orbital, p orbital, d orbital, and f orbital are going to have is also very important. For s orbital, the maximum number of electrons it will have will be 2. It must not have more than 1 electron. in these two electrons, one electron, if I'm going to draw the shell of it, one electron will face up, another one will face down. P, we have 6 electrons as maximum number of electrons. It must not go beyond 6. D, we have 10 electrons, and we have F is always going to have 14 electrons. If you look at this arrangement I have shown you so far now, you discover that there is difference of 4 in between each of these terms that we have here. So in that sense, just look at it that there is difference of 4. Once you know the value of the maximum number of electrons for the s orbital, just continue adding 4 to the remaining, then you get to the F. Now, after you've been able to get it, then how do we fill this into the different element? I'm going to start from hydrogen. So I want to start from hydrogen. I'm going to start from hydrogen is having 1 electron, now having 1s1. I'm going to follow this string now. Helium will be 1s2. Don't forget, I've been able to complete this energy level of 1s now. Now, followed by lithium, which is what? 1s2, 2s, you can see it's 2s that is next A, 1. Beryllium, 1s2, 2s2. Boron, 1s2, 2s2. This s orbital has been fully filled again. Then you need to spill to the next one, which is going to be what? 2p1. Carbon is 1s2, 2s2, 2p2. Nitrogen, 1s2, 2s2, 2p3. Oxygen, 1s2, 2s2, 2p4. If you count this very well, you see that the atomic number of oxygen is 8. Fluorine, 1s2, 2s2, 2p5. You can see that this p orbital is yet to fully occupy. Neon, let me get it. Neon is 1s2, 2s2, 2p6. Then after neon is sodium. Sodium is 1s2, 2s2, 2p6. You can see you have 2p6 here. Then followed by what? 3s1. You can see sodium is 11. It's 2 plus 2, 4 plus 6, 10 plus 1, 11. Sodium, magnesium, 1s2, 2s2, 2p6, 3s2. Aluminium, 1s2, 2s2, 2p6, 3s2. You can see we have been able to fill the 3s fully now. 3s2, then followed by what? 3p1. Silicon, that is 10, 13. Silicon is 1s2, 2s2, 2p6, 3s2, 3p2. Phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. Sulfur, 1s2, 2s2, 2p6, 3s2, 3p4. Chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. Now let's count fluorine. That's 17. Yes, that's right. Argon. Argon is 1s2, 2s2, 2p6, 3s2, 3p5, 3p6 now. 3p6. Potassium. That's a 1s2, 2s2, 2p6, 3s2, 3p6, followed by 4s1. Calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now, you can see that the 4s2 is the last value that we have there. So it stops here. The first 20 elements of their electronic configuration stop at that level. Right now, I want to show you just how to show that this energy level of few of this element. For instance, this energy level for the arrangement of energy in that of lithium, for instance, lithium will be in form of, this is 1s. This is the 2 electron, how they are going to fill up into that orbital, then 2s1. 2s1. Now, what I am interested in showing you here is how these electrons are filled into this orbital. Now, there's a rule that tells us that electrons are filled into the orbital singly first before pairing takes place. So let's look at how that one used to be. Let me also talk about the nitrogen now. Nitrogen, you can see this is nitrogen here. This 1s2, 1s, this 2s, 2s2 again, 2p3. Now, the P, we have 3 subshell because each of them will be occupied by 2 electrons. It will have 3 subshell. The first shell in this order now, this is 2p3, will be filled this way. 1, 1, 1. It will be singly filled first. This is what we call singlet filling. It is singly filled first. It is filled one after the other. That is, you must fill each of these orbital 1, 1, 1 first before you start filling 2, 2, 2. Not that you just say, you want to write nitrogen and now say 1, 2, 3, 4, now say 5, 6, 7. No, that is wrong. This is the correct filling for the nitrogen. And let's talk about talking about oxygen now. Oxygen will be in this order. This is 2p, 1s2, 1s2, 2s2, then 2p what? 2p4. This is it. 1, 2, 3. Then the fourth one will now comes like this. 2p4. That is how it's going to be. 2p4. Then that one over. Let me also talk about carbon. Carbon will be equal to 1s2, 1s, 2s2, 2s, and 2p what? 2p2. That'll be 1, 2, 1, 2. That is how you are going to fill it in order of that nature like that. Don't forget, as I've told you, electron will fill 1, 1 when they are in 3. When they are filling into the 3 sub shell like this, they will fill it 1, 1, 1 first before they will start pairing with one another in that order as well, like that. So that is how you do your fillings of a kind of a energy level of electronic configuration. It can be asked a question and whereby a particular energy level will be shown to you, and you'll be asked which kind of element are they talking about there. Take note of that very well. We'll see you in the next class. Please do subscribe to our channel so that you'll be able to have detailed information from us on a daily basis. Thanks and God bless.